Howdy guys. How many of you were in the Firmware 101 class? One of you? Two of you? Okay. You didn't learn anything there but you need to know here. So you got that going for you. The last class was basically just to kind of give you an overview of software versus firmware and kind of throw a bunch of buzzwords at you. In this class we're actually going to write some code, or at least you're going to look at some code examples and see what you can do with that and figure out where to extend that. So with that said, we're going to install some software, which all of you are diligently working on now, I believe. We're going to talk about why I chose not to go with the Arduino IDE and instead go with Atmel Studio, which is obviously giving us some grief tonight. Talk about some tips for success. We'll go through some first steps about getting your Arduino IDE to start blinking, and then we'll talk about how we can take it further. So first of all, you've already seen this slide. Just want to make sure we're installing the software. On that directory of stuff that I gave you, there was a couple of things called avr-libc-avrdude. It'll probably work out best for you if you stick it just right on the root of your C drive. You can delete it off there later or move it somewhere else. If you choose not to put it in C, just you'll have to change the path a little bit later, but it's not a big deal. So we're targeting an 8-bit microprocessor. So why not use Arduino, the Arduino IDE? So the Arduino IDE is a great place to start. It abstracts a lot of things where you can use pretty much the same code on a bunch of different microprocessors. The IDE is super simple. There's nothing to it. And you don't have to think about multiple files or file management. Well, some of these kind of are its downfall in some ways. Since it abstracts a lot of the finer points of your microprocessor, you lose some of the granularity. I mean, you can still get it, but I feel that it's better to know some of the low-level stuff so that you can do more interesting things with your processor without having to keep running into little holes in the Arduino setup. The IDE is super simple, but if anyone's used a modern IDE, you're probably going to be kicking yourself using an Arduino IDE after a few minutes. I mean, the semantic sugar of being able to right-click on something and go find the definition is really nice, versus having to Control-F and hope it's somewhere in there. And the Arduino IDE really kind of wants you to put everything in one file, or at least a lot of people end up with that. So you end up with 5,000 lines in a file and scrolling through it trying to figure where everything is. Anyway, the question though is, so what's a good IDE to use then? I'm sure most of you guys are hackers. You've probably made a website in Notepad before. That's pretty cool, right? So it's nice to have that power to go in and do it. If you've looked through like the HTML that like Dreamweaver or any of those kind of things spits out, it's awful, absolutely awful. So being able to do it with Notepad is really nice, but you lose some of the ability to have syntax completing and highlighting and such in Notepad. So, a bit of a spoiler, we're going to use Atmel Studio, which is a nice IDE. I swear to you, it's a nice IDE if you guys can get it installed anyway. It's based around the Visual Studio IDE. So it has nice things with highlighting, and you can jump through definitions really easy, and it makes life easy anyway. So with that said, under the hood, both Arduino and Atmel Studio, both use avr-libc, which is an open source bin utils for the AVR processor, or at least for the AVR processor. Different architectures may have different bin utils. So bin utils are basically the utilities for doing all your compiling, assembling, linking. It also includes the standard libraries for things like standard IO, printf, malloc, those sorts of things. So little things we take for granted, someone had to write somewhere. So that's what libc does for us. The other thing it includes is avr-dude, which is the AVR downloader and updater, or uploader. So it handles all the communication with your processor through several different bootloaders. It's not actually included in Atmel Studio. It's part of libc. You can compile it yourself, or it's included with the Arduino IDE. So I stole it out of an Arduino IDE and put it on the flash drives to pass around with all the malware. So make life a little bit easier. So let's talk about a few tips for success in developing your first firmware, or really any firmware. First thing you want to do is know your schematic. You want to take a look at your schematic and figure out how are things wired up. Does a pin need to go high, or does it need to go low to get an output? Where do the pins go? So even if you don't really know how to read a schematic, having a general idea of where the lines connect up is very helpful. Next thing you'd like to have nearby is keep the datasheet for the part you're working on handy. Datasheet has a lot of useful info in there about configuring pins and alternate functions and gotchas. Most chips have an errata section in there where they talk about, well, if you set this bit after you set this bit, bad things is going to happen. So instead of pulling your hair out, it's useful to look through your errata and figure out, oh, if I do that, I'm going to be up all night trying to figure out how to do this. You also want to make sure you use comments and be verbose about your code, because I guarantee 6 months from now that clever code that you hacked together 3 beers in is really going to make you mad at your past self. And finally, when you're coding, work on one function at a time. It's very tempting to write a lot of code and do everything and then hit compile. And the times that I've done that and it's compiled and it's worked have always freaked me out because I feel I'm missing something. It's a lot easier to do one little thing, flash an LED or do something small, compile and test and test and test until you're really happy with it before moving on to the next thing. All right, so the hardware we're going to use tonight. Pictured here is an official Arduino board. If you borrowed a board from me, you got a cheap Chinese knockoff. So it won't quite look the same. The Arduino board notably is using an Atmel processor up here for the USB interface instead of some other interface, cheaper interface anyway. So it's really like having 2 AVRs in the same board, but we're going to be programming the little 8-bit microprocessor here. And since you guys, luckily I made enough boards, and everyone got a Shield board here that has the fancy, good thing they're made out of fiberglass, has the fancy little DC801 Crossbones logo here, or at least I hope everyone got one of these. Did anyone not get one of these? Well, you're in luck. I still have a couple left.
What's up, Mike?
So nothing fancy on here. It's just a breakout, some flashing LEDs, or some LEDs you can blink anyway, and a couple of buttons to press. But at least it'll kind of get us started on having some interesting feedback on getting your Arduino going. All right, so let's take a look at the schematic for the Arduino Uno. There's a lot of lines there. There's a lot of things. Seems pretty complicated, so what we want to do is kind of see if we can break it down a little bit. First bit, this big block of stuff over here, this is just a USB interface. Got your USB port, there's that chip I was talking about, so you can pretty much ignore all this. That makes it a little bit easier. Up here is the power supply, so all this guy is doing is just taking the 5 volts and dropping it down to 3.3 volts, so we can mostly ignore that. There's a power select piece up here that determines is the power coming in through USB or through the barrel jack. Okay, we can ignore that. There's a blinker here. That might be interesting. It's got an LED that we can control right on the Uno. Here's what we really want to deal with is the microprocessor that we're going to program. So all the microprocessor outputs are all tied to these I/O here, which is the sockets around the edge of a board. So that gives us an idea of where each one of these pins ends up on that header. And the final thing you want to look at is the clock. For some of the timing and delay functions, it's good to know how fast the chip is clocked. In this case, it's clocked 16 megahertz. So let's take a look at this 801 Shield that everyone got. So, same thing. Let's break it down a bit. First piece is this symbol is just a breakout of all the pins on the top side, and we're not using most of them. So you've got your blinkies over here, your single LEDs. These are two eyes that are on there. They're RGB LEDs, which means that each one of them has a red, green, blue, so that you can make any color with them. And then finally, there's a couple of buttons up here that you can press to have some sort of input into the board. So if we simplify it and break it all down here, what we really have is our 8-bit processor connected to some LEDs. So from that really complicated schematic we started with, this is really all we care about for what we're doing for programming. And in particular, we care about these ports. On the AVR processors, they like to group things into 8-bit ports. You notice this one has 7 pins. Start at 0, because that's the only way you're supposed to start is at 0, right? Up here, we only go to 5. And the trick is these crystal inputs over here are 6 and 7. So sometimes on these ports, there will be pins that you can't actually access. Unless, you know, if you're doing the RC oscillator inside instead of the crystal, maybe you could access them then. So, set up your Uno if you haven't already. Hopefully you plugged it in, drivers got installed, didn't have any issues with that. Even if if you don't have the shield on there, or even if you do have the shield on there, you should right now just have an LED blinking. Did everyone get to that point at least?
It's blinking.
And so you know, the blinking doesn't necessarily mean that the driver got installed. It just means it has power. All right. Is anyone else got Atmel Studio installed at this point?
It says it is, and I'm trying to open it. Let's see.
It takes a long time to launch.
I'm still compiling avr-libc. So
You may be in the wrong class.
it's gonna be a minute.
Still dealing with the Visual Studio Shell thing. Got nothing. Can't find a download for it because Microsoft sucks. They hide everything. It's Bluetooth.
Where did you get them from?
Jared, Fed, what's his name?
Yeah, I know.
He bought like 6 of them or whatever, and I bought one off of him for $10.
I mean, I'll just cut it after.
Okay, fair enough.
I usually just leave it recording and then we cut it to take out stuff like waiting and stuff like that.
Install?
Oh, okay.
Where's the flash drive? Oh wait, you're on Mac.
That's
You have
okay.
a Windows again?
Windows.
Okay.
Do you have a USB-C adapter too?
I do.
Is there more malware?
Because he has one of those really fancy laptops that doesn't use USB-A anymore.
Does anyone else need a USB-C adapter?
Hey, there you are. Hi, Jared. That's not my name.
That's not his name either.
Mr. Ged.
Still working on it.
Who is it that started calling you Mr. Ged?
That would be Duzzy.
I thought it was Lost.
No, that was Duzzy.
There's already a newer version of Microsoft. Okay, so how do I get the Visual Studio thing?
It'll probably work the same for you.
Visual Studio.
So it's not a separate installer, it's an isolated installer of Visual Studio, so you can create applications that use some of the commands without people having to install it separately.
What?
That's what the isolation installer is, so you can include
Okay,
that
but
stuff with your installer.
I can't find the installer.
No, their error message is garbage. There's not a separate installer pips. Do you not understand me?
Okay, well, it's also not completely garbage because it won't launch.
No,
It's
that's
not finished installing.
that's what that
Somewhere over here.
that is. Visual Studio isolation is literally the components you include with your application, so that people don't have to install anything external. Their error message doesn't tell you what's wrong, so it's garbage. Even if you open the logs and look at the logs are
I
garbage.
already got toasty.
I worried a little bit if my cheap flash drives didn't have some issues, but I tested with some other flash drives and it didn't seem to be the issue. So
Sorry. On that flash drive, install all the stuff on there.
Where is it?
On the flash drive.
But where's the flashlight?
Oh. I thought we gave you one.
You had it in your computer bibs. Because you're special.
It's too warm in here.
Does anyone have an extra USB cable?
Yes.
Sweet.
I have an extra Uno too. if someone needs it.
Promise to come back.
That's fine.
So how much were your Chinese using Linux?
$8.
Can I PayPal you $8?
Yes.
Okay,
Big deal.
I'll do that.
Yeah, I think this is cheap.
What's your PayPal?
Huh?
What's your PayPal address?
Hamster at snurkle.net.
Hamster at
Snurkle.net.
SNERKEL.
SNURKLE.
You genuinely expect people to like.
It works for me. I don't know what
That's why I
your
like
problem
my
is.
domain. Pip.rocks is awesome. So I actually can't receive email on any of it, so.
Yeah.
Looks the same to me.
I don't know, I mean, I've owned the domain for like 4 years.
That's the other one.
Dealing with mail servers is lame.
So you just like register through a company like Silent and then give you a free
Like some shitty
email forwarder.
Well, that's what
Forwarders are
Google
great, but
Domains does.
I want to be able to, yeah, then I have to transfer it.
No, Google Domain does forwarder, or you can just set your MX records to go to your own.
Oh, then I have to pay for it.
Pay for your domain? You already pay for it.
Pay for the mail.
Or set up your own mail server at your house.
That's the annoying part.
Just let me host my own mail, damn it.
They do.
Well, it's online for free.
All right. Well, anyone that actually did get the Atmel Studio installed, you can go ahead and go to this next step here. You'll want to go up to Tools, External, and this is assuming that you put avr-libc-avrdude on your C drive. If you didn't put it on your C drive, just adjust these two paths accordingly. Also on that drive I sent you, there was a text file in that same directory that said the arguments to external tools. And these are those arguments, so you don't have to copy off the screen here. You just cut paste out of that file. So all this is going to allow us to do is that then you just have a menu option you can click on to flash your Arduino, so you don't have to do it manually. The other option is you may already have compiled code in the code examples. I can't remember if I put that in there or not. If you can't get Atmel Studio installed, you could just flash the hex files on there and see what the different programs we do are going to do look like. So there's that option as well. Is your web installer kind of close to getting done, or still kind of stuck? Is anything working out for your computer?
It's restarting right now.
Okay.
So, fingers crossed.
We'll give it a few more minutes.
Okay. Copy everything. I'll start installing.
Oh, and the final thing for this, it says COM3. If yours is not COM3, you might want to adjust it. If you go into the Windows device driver and look at COM ports with your Uno plugged in, it'll tell you which COM port it's assigned to.
You need a Windows admin.
There's a handy text file with all this
Weren't you in Windows admin?
Yeah. I didn't want you guys to have to read it off the screen. I mean, geez, that's lame, huh? What's that?
You're not quite that.
Yeah, not quite, not quite. I'll only make you install this giant binary that doesn't work on most computers, so.
It's because it's a Windows binary. If there were like a Linux alternative,
There are,
My kernel doesn't support it. Let me just recompile it.
Do we need to
there's some
install-
decent alternatives
I think
for
so.
Linux for doing this sort of
Just the
thing,
first one
but
I did.
most people
And
that
then
show
go
up
for
to
the
this class
tools.
show up with Windows,
Yes.
so I decided to target Windows.
It was probably a good choice. I just debated.
Under Linux, you can use GCC straight up.
Yeah.
You can pick the IDE of your choice and set up a make file so you can do all this. You can do a similar thing on the Mac, actually. You can use Xcode if you want as your IDE or whatever you want to use, and you can set up some make files to just compile GCC. So that's really nice. It is possible to use GCC straight up under Windows. I only chose the Atmel Studio because I figured it would be easier to set up with a group of people, but I'm being a little proved wrong on that one. So.
What's with our network today? What's with our network, Pips?
I don't know. You're
There's a
the
lot
one
of
having a problem with it.
It's just all the signals.
Yeah, we're all trying to update Windows locally.
I'm not even running on it. I'm running off of my phone because of it.
These are really cool. Did you hand solder all of these?
Yes, I did.
Boy, especially those I ones.
So
You didn't reflow that?
I did reflow it by hand with a toaster oven.
Yeah, I saw your
Hamster's toaster?
tweet that you did baking
Not for
for the
food.
class.
Well, yeah. These little boards. What I do is I've got the soldering station. I've got an air dispenser for solder paste. So apply a little bit of solder paste in each of the pads, and then use some tweezers to place all the components, and then put them in the toaster oven, and then you have a reflow profile where you bring it up to a certain temperature, hold it for a little while, and then bring it to a different temperature for the. Basically, you're baking all the moisture off, and then you're activating the flux, and then you turn the toaster oven all the way up for about 30 seconds, and all the solder melts. And then I was doing them 6 at a time, and then after that was done, go through and fix the little issues. Those top resistors, some of them like to kind of flow together, so I had to go in and fix them manually, and then the solder all the pins on.
Where did you have these PCBs made?
From Seed Studio,
Yeah, they're cheap.
really cheap.
I just have some orders made, so I didn't order it.
Yeah, I think I ordered 40 of these boards, and I think it cost me something like $45 for 40 of them.
If you order more, they'll get cheaper.
Yeah, they have a screaming deal on Proto. You could do 100 millimeter square boards. You can get a pack of 10 of them for $4.90.
That's awesome.
So that works really good for prototyping.
Oh, Seed's the one that makes that soldering station and stuff.
Doesn't Seed make the really cool LED like matrix things? Like 8x8x8?
They might. They have like a whole shop where they sell all kinds of stuff. They're based in China, obviously, because all the best things come from China these days.
All the cheapest things come from China.
Right. Yeah.
Best is probably not the right answer here.
Best
Yeah.
for the money.
But it always amazes me because I can submit an order like Monday night, and DHL is texting me the next Monday saying that they're ready to deliver. So it's always very amazing.
Who's this doing the thing?
I'm doing the web installer. See if it works.
All right. Well, maybe we'll move forward to the next step here. Did everyone get this external tool thing configured? All good to go? Any issues there? Except for people that are waiting to install.
We're good.
All right. So we're going to do a really simple blinky, which you pretty much already have. So in the code that I gave you, go open step 1. If you scroll into the directory a little ways, you'll find the project file, which will be like have a little red bug icon, and that should open right up in Atmel Studio.
And step 1.
If it doesn't show the main.c, if you look on the right hand side of the screen, let me hop out of this thing for a second here.
like to install this? Sure, you can install some crazy virus.
Only if you got the pink one, is there a virus on it?
Oops.
So
Breast cancer awareness.
I took a snapshot before, I'm good.
So if you open this file here, this ATSLN, if you don't see anything, if you look over here on the bottom of this screen here under Solution Explorer, it'll allow you to find all your files so that you can open the main file. So at this point, you got your code there. Let's see, well, I've got it on the screen here. So the next thing we want to do, if I can, yeah, okay. Next thing we want to do is build it and program it. So if you go to Build Solution, or press F7, the bottom message window will scroll a little bit. You should end up with it compiling successfully. Let's see here. So you should end up with a build succeeded. And then make sure your Uno is plugged in. Go up to the Tools menu option and choose the avr-libc-avrdude option that you just created. You should get a terminal window should pop up. If it pops up and goes away immediately, you have your path wrong or your COM port wrong. But it should pop up and remain for just a couple of seconds. You should see the LED on your Uno will stop flashing briefly, and then it'll go back to flashing. And that means that you successfully flashed your first code onto your Uno. So, pretty easy once you get it going. Did it work out for anyone? Yeah?
I'm trying the web installer.
All right, let's talk a little bit about what happened when you pressed build there. So when you hit build, GCC took your code, the main.c, and compiled it down into assembly code. And then AS, which is the GNU assembler, converted that into object code. And then LD took the object code and linked all the objects together and figured out the offsets in memory where everything needed to lie. And then it ran obj-copy, which copies the object code into hex output. And then finally, avr-libc-avrdude flashed the chip. So a whole series of things happening there under the hood for you.
Who wrote avr-libc-avrdude? Like, is that like something the chip manufacturer made, or?
It's part of the avr-libc. It's an open source project.
Okay.
So I don't know if there's any one person that wrote it.
Got it. Okay.
But standard GNU world of open source, right? Good question back there?
Yeah. Are there any good books that you would recommend as far as some of the undeveloped details?
Good question. Most of my stuff comes from looking at things on the web. Things tend to change quickly enough that usually you get a little bit more accurate information looking at resources on the web. I don't have anything good that I can recommend you off the top of my head.
USB passes through.
Hit me up on Twitter.
Even if it's serial.
Yes. I am Hamster on Twitter, so
Oh, gotcha.
feel free to send me a message if you have questions later. So, looking at the main code, let's talk about it a little bit. There's probably some stuff in there that looked a little weird, especially if you've done some Arduino stuff in the past. First thing you probably noticed is that we had something that said DDRB and port B, and we had some hex numbers going into those fields. So what does that do? From the chip documentation here, you have to configure all the pins in your processor to figure out what you want them to do. And since we're going to use some pins for GPIO, we want to look at this section. First thing we want to do is we want to set the data direction register, which says which way are we going to be using the pins. Are they going to be configured as an output, or are they going to be configured as an input? What we're seeing here is on port B, we're going to use the lower 4 bits, the lower 4 pins, and the upper 2 pins. So there's 6 pins that we're going to configure as outputs. And the rest of them we're going to configure as inputs. We actually don't care about them in this setup. And then the next piece of it here is we want to set these pins high initially. Why do we want to set them high? Well, if you looked at the schematic, what you would see is that the other side of all the LEDs are tied to ground, or tied to VCC, I'm sorry, tied to high voltage. So by setting these high, then you're not putting a voltage drop across the LEDs and they won't turn on. The reason why it's usually preferable to set it up so that you drive a pin low to turn things on is that your processor can sink a lot more current than it can drive. So on the sink side, you might be able to, the processor might be able to handle like 100, 200 milliamps of current through the processor. If you're trying to drive a high signal out, it may only be able to handle 10, 15 milliamps worth of current. So it's really easy to burn up your microprocessor if you're not careful about how much power you're passing through it. Does that make sense? And do feel free to stop me and ask me any questions at any time. So the next piece of it was, how do we do the weighting? So there's a nice little built-in function in avr-libc that's called delay ms. And what this is it's basically a macro that takes the CPU frequency and figures out how many no-ops it needs to execute. So this is what's called a busy wait. So even though the CPU is waiting, it's not technically waiting, it's just busy doing something. It's like scrubbing the floor for a second or two. Not so good for power usage. The CPU is going to be going balls out the entire time that it's doing this waiting loop. But if you don't care about power, this is a great way of doing busy waits. The nice thing about this, if you turn off your interrupts, which we don't have any interrupts enabled, this is very deterministic timing. So we know from the chip doc you can find out exactly how many jiffies it takes, how many nanoseconds it takes for each operation to execute, so that you can make it delay for an exact amount of time. So this is the basis of doing real-time code, is being able to know exactly deterministically how long something takes. So the next piece of it here is all this bit shifting here. What's up with all this? This looks kind of complicated. So what we're doing to set a pin low is the first thing we do is we read the current port, what port B is currently set to. We take a 1 and shift it 5 places because we want to set pin 5 low. So now we end up with a hex number that looks like this, which would be 0x10. And then we bitwise invert it, so you have that single bit becomes a 0. Then you bitwise and what port B was before with this mask. And what this will cause is anything that was a 1 in port B that's also a 1 here will be a 1. And whatever was in pin 5 here, if it was a 1 before, now 1 and 0 is 0. So it's going to set that bit in the port low, and we write it back out to the port. You end up doing a lot of bit shifting when you get down to the low level of things. We'll make it a little bit easier here in a minute, but just for the moment to give you an idea of what to do there. To set something high, you end up using a bitwise OR. Same sort of thing, we're going to shift a bit over, we're going to OR it with what's currently there, but set the port back out. And that'll make that, that particular bit high. Does that make sense to everyone? So, with that said, pound defined is your friend. It allows you to turn something complicated like this into something that's mostly human readable. So, this will save your sanity over time. You do have to be a little bit careful about abstracting too much things away, because then it gets a little bit cumbersome, but with proper use of it, it works out pretty well. Alright, with that said, if we move on to the step 2 project, is anyone still having issues installing? You getting anywhere with your install? No?
It's working on it. It's updating Visual Studios now.
So the error message that everyone's getting, the 2515 shell isolated error, is because Windows, if you haven't finished your Windows updates and it's waiting for a restart, If you look back in the error messages, it says your system is pending a restart. So if Windows isn't properly updating, then go repair your Windows update, and then it will work.
Also, you can do the web installer, just not on our wireless. Use your phone. It's faster.
It's fast.
It failed when I did that. After I did this.
Okay.
So
Cool.
So, yeah, overall, if I'm gonna try to push forward a little bit more on here, if you guys can't get it installed or whatever, you do have the PowerPoint, and I can talk to you more about going through some of it later. So, but make sure you won't get too behind, but try not to delay the class too much here. So, looking at the Step 2 project, so if you open this project, this does exactly the same thing as the Step 1 project, but what we've done is we've created these defines for us that allows us to say which address and bit we want to set, so that in our code here we could define that the upper right yellow LED on the shield is in port B pin 5, so that all we have to do is say clear bit on that, delay, set bit on that, and away you go. So,
And the clear bit would turn it on because you're sending it low, right?
correct. Yeah, clear bit, clear it from 1 to 0, set bit, set it high.
and that makes it
I listen.
Excellent. I like it when someone listens.
the first time you've ever done it.
It might be.
What?
So this project does exactly the same thing as before. You're welcome to compile it and flash it out to your processor to prove it to yourself, but you'll see the same thing.
Alright, let's see.
And so the define.
Looks the same.
Okay. So you do have to
Should be
define
flashing
what your.
faster.
Should it?
Did you get avr-dude set up?
Maybe I got that wrong.
I can't tell if that's actually working or not.
All right. Well, if we move on to step 3 here, let's see, is this the right one? Well, when we get to step 4, you'll know for sure if you've got it working or not, because we're going to change up what we're doing. So, step 3 here, the next project, what we've done is we've taken these routines, which I borrowed those routines, the defines from this forum link, moved them into some header files. So to clean up our code here, so we can get down to the nuts and bolts of what we're doing without having all that stuff cluttered up. But having a nice IDE makes it easy to get into those files to edit them. So this does exactly the same thing as step 1 and step 2. It's just, progression. So step 4 project, if you want to open this one, we're going to do something different this time. For step 4, what we're going to end up with, let's see here. Oops, wrong thing. So when you compile step 4, what you should see is each one of the LEDs in your shield is going to flash in turn. So we're using the same sort of stuff as before. We're just using a big switch statement here as a state machine to figure out which one should be flashing now. So basically, your programs are going to always take the state of, you're going to have one big while loop that just continues doing this over and over. If you didn't have this while loop, it'll execute once and then run off to the end of the world and your processor will halt. So this switch statement here is just being used as a state machine. What you can't see is that current LED is just an integer that's defined up here. So each time we go through one case, so if current LED is 0, then we're going to blink this LED and we're going to set it to 1, and then fall out of here, come back around, and so on and so forth. So it's going to blink each one in turn and just kind of work its way through a state machine. So when you're doing embedded code, you end up with a lot of state machines. And there's lots of different ways to tackle state machines, but this is a pretty basic one, just using a switch statement. Anyone getting any flashing going on like this? Yeah? Excellent, excellent. You having issues over there?
Yeah, I probably missed a step.
Okay. Is that where you put, okay. Did you put,
It's so rare that we see
AVR-libc
Lean
comp?
to go see
Is it in here as well?
Right, C drive.
Okay, you got the C drive,
Yep.
and then, your
That's a
Arduino
badass
three.
fucking sword.
Okay, so it's
That's not
different
just
here.
like, God, that is so ball ninja.
Okay. That's good.
Oh my God,
There's
that's
scrolls
awesome.
over to the right. Let's make sure we got it all. Oh, you're missing some stuff.
Okay, that would be it then.
Oh, yeah, you got line ramp on there.
That's awesome.
Okay, I'll fix this. Thanks.
All right.
Encourage
Anyone else have
this.
any trouble flashing the number 4? You got it figured out?
I'll
Okay.
let you know when I get there.
You guys getting close to getting
Maybe.
getting close?
I'm just waiting for this to finish and still error and just quit.
Mine
I'll just
did.
quit.
After I did that, when I did the web installer. Mine's something up with Windows updates, I'm pretty sure.
My Windows updates are all good.
I'm missing Marches apparently.
I know, I put like.
If you want, I can build yours and push it too once I get mine working.
I mean, I'm giving mine back anyways. So it's more just.
All right.
like
So,
building the code.
any questions at this point about where we're at so far? All right. So let's move on to the next step here. We're going to talk about inputs. So first thing you should know about inputs is pull-ups are important. So your microcontroller here can only read high or low. It can't read floating. It doesn't know what floating means. It needs to know either that it's definitely at a low level or definitely at a high level. If you have something that's just floating, like if this wasn't here and this is open, this input will float, and it may do what you want it to do some of the time, but if you get enough like static charge build up on this pin, it could sit there and toggle back and forth, or it could be on or it could be off. So pull-ups are very important. The good news is almost all the ATmega processors have a built-in pull-up that you can configure. So when you define the port, you can set it so that you enable the pull-up resistor built into the chip. So if we take a look at the Step 5 project, we've added some more stuff in here. So in our while loop, what we're doing is we're checking to see if the right switch is pressed. If it's pressed, for the Step 5 project, they're not going to blink in sequence like they did before. Only one is going to blink. And the right and left switch will allow you to advance or go back to the previous LED. So basically what it's doing is it's looking to see, is the switch pressed? If it is, then we'll go up one LED. And then this guy here, all it's doing is if we go beyond the end of 4 LEDs, we just loop back around to the first LED. It can be really easy to go off of the end of your array, and then things get very strange. It's like, why doesn't that work?
Sounds like there's a story behind that one.
Yeah, the story of my life is it's a off by 1 error, you idiot. So once it's flashed on there, you should be able to press buttons on your board here to toggle between the different LEDs. Hey, looking good. You got avr-libc-avrdude working.
Yeah.
Everyone else getting this working okay? All right, let's. I'm sorry. So let's talk. Was there something else there? Sorry. Okay. Let's talk about some problems we have with this current setup. You'll notice that sometimes when you press a button, it doesn't really do what you want it to do. So why is that? So part of the problem is that the button isn't read until after the LED blinks. So you have to wait for the LED blink to complete before it comes around and reads the button. Yes?
So is that like a no-op timing issue?
Somewhat. Since the CPU is doing things very serially, so it's kind of like imagine you're making some toast, right? So you go and you stick the toast in the toaster, and then you turn around to get the butter, right? Well, I don't know where this this metaphor is going exactly. I thought I'd work it out.
I was just wondering if you pushed it on a no-op, then it would be like, oh, well, I'm not registering it because I'm on a no-op, and now I'm
Right.
in a pause state. Okay, so
Yeah.
Okay.
So when you're inserting the toast into the toaster, you can't, unless the refrigerator is really close by, you can't also get the butter out of the fridge. You have to get the toast inserted and then get over to the fridge. And once you get to the fridge, you can't put the toast in the toaster. You can only do one thing at a time. There's where the metaphor was going. I knew it was there somewhere. I often get confused by my own metaphors. I do admit that. So that's one problem that this code has, is that it has to do things in a very serial fashion. Some of the workarounds for that sort of thing is to have much shorter delays. Like you could set it up so that, okay, I'm going to delay for 1 millisecond increments, and between each delay I'm going to say, is that button pressed yet? Is it pressed yet? So that effectively from the user standpoint, it reads faster and it seems like it's picking up faster. So that's one way to solve it. Another way is to use interrupts, where you put the button press on an interrupt so that when the processor detects a button press, whatever it's doing now, it's going to pause and jump to an interrupt. We're not going to talk about interrupts in this class. That'll be the next class. But it gives you an idea of where we're going to go with that. The other problem we have, and you're not going to notice it so much in this by virtue of having to deal with that busy wait, if we had an interrupt, you're going to see issues with a button not being debounced. So what does debouncing mean? Well, even though you're pressing that button down, and you're pressing it good, and you're hearing it click, what happens is as it comes down, the contacts bounce just a little bit, and there's a slight amount of time where there's an indeterminate state, where it could be high and low a couple of times on and off before it's finally really on. And you'd never notice it, but your processor would notice it. So if you had it set up in an interrupt, you might see that one button press ends up to it being triggered 2 or 3 or 20 times, right? So you'd want to debounce it. So let's talk about debouncing. So to debounce this, what we're going to do, and this is in the step 6 project if you want to look at it, is we're going to add in, this is a software debounce. It's possible to do a hardware debounce with a capacitor and a resistor for an RC time constant, but you can solve this pretty well in software as well. What we're going to do here is we check to see if a button is down, and then we're going to wait 5 milliseconds to try to give this guy a little bit of time to finish debouncing. And then we're going to read it again. Is the switch still pressed? If it's still pressed, then we're going to say, hey, it's pressed. And then we're going to move on. So the idea is that this delay is long enough to cover most debounces. It's not going to cover all of them. There's some, like if this has 10 milliseconds worth of bounce, then it's possible you could get in the middle of this and it wouldn't be what you're looking for. But so you're going to have to play with that a little bit for most of your user cases. But this works pretty well. So otherwise, 5 milliseconds, the debounce is passed. We're going to read, is it high? Yep, it's high. We're going to go ahead and set that and move on. Another thing that you would usually do at this point is you would then pause and wait for the switch to be released. As you've probably noticed right now, if you press and hold a button, it'll go through all the LEDs. And that may or may not be the behavior you want. You may want it so that you press it and it just advances to the next one and stays there, right? All right, so that's pretty much the wrap up for this class. So next time around, we're going to talk about interrupts and pulse width modulation. And you guys can play with the code on your own a bit and figure out how to make the eyes light up. Next time around, when we get into PWM, we'll figure out how to make it so that they're not blinding. The eyes ended up being a lot more bright than I thought they would be.
That's the best type.
So, any questions or snide comments?